Layered oxides. Statue of Liberty is an example of layered oxide. Have you ever wondered why is the Statue of Liberty green?
The Statue of Liberty, the symbol of freedom and liberty and America and everything that's great about this country. There she is, Lady Liberty, standing there in all of her blue-green glory. But she wasn't supposed to be this color. The Statue of Liberty was a gift from France back in 1885 as a way of commemorating our fight for independence and their own aspirations towards democracy. This 305-foot statue was built over 9 years in sections of copper skin on top of an iron skeleton. According to the National Park Service, the statue has about 30 tons of copper, which is enough to make 435 million pennies. Yes, bright reddish gold pennies. But the Statue of Liberty isn't the same color as, well, any penny I've ever seen. So, how to explain Lady Liberty's color change? Simple. You change colors too if you stayed outside in that New York City polluted air for almost 150 years. I'm kidding. Well, mostly. It all comes down to chemistry. During her first few decades in the Big Apple, the statue slowly turned from that shiny copper color to a dull brown, and then finally to the blue-green, or as they say back in France, verdigris that we see today. Officials suggested trying to restore her to the original color or painting her, but after a public outcry, they decided to leave her the way she is, and she'll continue to look like that until Dr. Zaya shows up. Anyway, her color change happened because of oxidation reactions between copper and the air. Now I know some of you smarty pants might be saying, well, duh, but copper's patina is more complicated than just one reaction. It's due to about 30 years worth of oxidation reactions creating a mixture of minerals. So let's get into it. Now when an atom loses electrons in a chemical reaction, it's called oxidation. This process was first observed in reactions that involved oxygen, hence the name, but it can happen with other elements too. The color change from coppery red to blue-green was bound to happen as soon as they parked her in New York Harbor. And here's why. First, there's all the oxygen in our atmosphere just hungry for electrons. Then you add all the elements in New York's polluted air into the mix and voila! In the first reaction, copper gives up electrons to oxygen. That creates this mineral, cuprite, which you can see is a pinkish red. Next, cuprite loses more electrons to more oxygen, forming blackish tenorite. The black color of this tenorite explains why the statue slowly got darker over the years. Now, let's pivot to sulfur reactions. Sulfur finds its way into the atmosphere through natural processes, including volcanic eruptions. But humans have also put a lot of it there too, with their boats and cars and pesky airplanes and factories. So when sulfur dioxide gets together with water, it forms sulfuric acid, which can form green stuff with copper oxides. Now, back to our color change. Lady Liberty gets painted with this sulfuric acid and her green color gets forming. Throw in some chloride from the sea spray around the statue's Ellis Island home and, well, you see what happens. Here's the chemistry breakdown. Tenorite, that black stuff, reacted with sulfuric acid and water to make blue-green brochantite. And thanks to New Yorkers, there was even more sulfuric acid in the air. So the brochantite became green antlerite in some places on the statue. Whenever the sea spray hit the Statue of Liberty and didn't get washed away by rain, brochantite sulfate got swapped for chloride and made olive green atacamite. So there it is, the beautiful and well-known blue-green hue. The Statue of Liberty has stayed this color for over 100 years because the exposed copper is now oxidized, and at this point of her life, she's stable. At least until she decides to take a walk. Anyway, the Statue of Liberty wouldn't be the same if she lived anywhere else. If nothing else, she has a New Yorker's thick skin, and has helped protect her over these years. So, what do you think?
So what are the properties of layered oxides? In summary, layered oxides possess unique properties that make them suitable for a wide range of applications. Their layered structure, tunable chemical composition, anisotropy, variable layer spacing, high surface area, interlayer ion mobility, and functional properties make them promising materials for various technological and scientific applications. First, the layered structure. Layered oxides are composed of stacked layers of metal oxides which are separated by layers of non-metallic atoms or ions. This layered structure gives them distinctive properties, makes them suitable for a variety of applications. High anisotropy. Layered oxides exhibit anisotropic properties, meaning properties can vary significantly depending on the direction within the crystal structure. This anisotropy can be exploited for specific functionalities, such as in electrical, thermal, or mechanical properties. Tunable chemical composition. The chemical composition of layered oxides can be tailored by varying the type and arrangement of metal cations and oxygen anions in the layers. This allows for a wide range of chemical compositions into diverse properties and potential for customization for specific applications. Variable layer spacing. Layered oxides often have variable layer spacing, which can be controlled by external factors such as temperature, pressure, or chemical doping. This can affect their properties, including their electrical conductivity, magnetic behavior, and ion diffusion. Next, high surface area. The layered structure of these oxides often results in a large surface area, which can be advantageous for applications such as catalysis, energy storage, and sensors. The large surface area provides more active sites for reactions, leading to improved performance. The interlayer ion mobility. Layered oxides can exhibit interlayer ion mobility, where ions or molecules can move between the layers. This can have implications for their electrical, optical, and electrochemical properties, as well as for ion diffusion and storage in batteries and capacitors. Here are some functional properties. Layered oxides can exhibit a wide range of functional properties including high electrical conductivity, magnetic behavior, catalytic activity, and electrochemical performance. These properties make them suitable for applications in fields such as energy storage, electronics, sensors, and environmental science. Now we're going to change topics here to the structural stability of layered oxides. Layered oxides are known for their structural stability, which allows them to retain their layered structure under various conditions. This stability is crucial for their long-term performance and durability in practical applications. Structure of layered oxides. Structure of layered oxides can be described as having a repeating pattern of oxygen atoms forming planes or layers, with metal cations occupying the spaces between these oxygen layers. The metal cations are usually octahedrally coordinated by oxygen atoms, forming a layer of metal oxygen octahedra. These metal oxygen layers are separated by oxygen layers, which would be either octahedral or tetrahedral. The arrangement of the metal cation and oxygen layers can vary depending on the specific composition and crystal structure of the layered oxide. For example, in materials such as lithium cobalt oxide, which is used as a cathode in lithium-ion batteries, transition metal cations, in this case cobalt, arrange in hexagonal close-packed HCP structure, forming alternating layers of cobalt and oxygen. In other layered oxygens, such as lanthanum nickel oxide, the metal oxygen layers can be arranged in a perovskite-like structure, where the metal cations are coordinated by oxygen atoms in a distorted octahedral arrangement. The layered structure of these materials give rise to interesting properties and functionalities such as high electrical conductivity, magnetic behavior, and catalytic activity. The materials have a wide range of applications including in energy storage, electronics and catalysts, and are an active area of research in material science and solid-state chemistry. The synthesis of the layered oxides. So now we're going to move on to synthesis of oxides. Synthesis of layered oxides typically involves several steps, which may vary depending on the specific type of layered oxide being synthesized. Here's a general overview of a synthesis process.
Copper metal and copper alloys often develop a blue-green coating called a patina when exposed to the atmosphere for a long period of time. Patinas are often seen on plaques, coins, and statues that contain copper. It is a copper patina that's responsible for the green color of the Statue of Liberty. A wide variety of compounds have been identified in copper patinas, and the formulas for a few of these compounds are displayed here. In this video, you'll learn how to simply produce a patina on a copper surface. Producing a copper patina is remarkably simple. I'm going to use these coins that contain copper, some aluminum foil, and a 9-volt battery. I'm also going to soak this paper towel in a mixture that contains 5 grams of table salt dissolved in 100 grams of household ammonia. After squeezing out some excess fluid, the paper towel is placed on top of some aluminum foil. Now the coins are placed on top of the paper towel, making certain they do not touch the foil. The positive terminal of the 9-volt battery is touched to one of the copper coins, while the negative terminal is touched to the foil. While doing this, I press down hard on the coin. If everything's working, you should be able to hear a faint hiss, which is due to the production of hydrogen gas at the interface between the foil and the back of the paper towel. Hey, look! When I remove the coin, a blue spot has formed on the paper towel. This occurs because copper 2 ions, which are blue in color, are formed at the interface between the coin and the top of the paper towel. I'm going to repeat this process a few times, and you'll note that blue spots are formed all along the paper towel. Once I've done this, I'll take the treated side of the coin and flip it up so it can react with components in the air to form the patina on the surface of the coin. This usually takes a little bit of time, so let's repeat the process with the larger copper coin while we're waiting. If you look closely, you can see that a patina is slowly developing on the surface of the smaller coin. Now that we've treated each coin, let's watch what happens as they react with components in the air. We'll place a shiny copper coin nearby for comparison. Notice that a patina gradually develops over time. The patina on the larger coin appears to be somewhat yellow-green, while that of the smaller coin is more green in color. Given that copper metal left outdoors usually takes several years to develop a patina, it is remarkable to watch one develop right before your eyes. Here's what the coins look like after 10 minutes. Kinda neat, huh? Let's see what happens if we repeat this experiment using a paper towel soaked in a different mixture. In this case, I soaked the paper towel in a solution of 6 grams of sodium bicarbonate, that's baking soda, in 100 grams of water. It looks to me like the spots formed are a lighter blue color than before, and the patina that develops looks somewhat blue in color this time. I hope you've enjoyed learning a little bit about the science of copper patinas and how to generate them.
So here's the steps for synthesis of layered oxides. So first is the selection of precursor materials. First step in synthesizing layered oxides is to select appropriate precursor materials. These materials are typically chosen based on their chemical composition and properties, as they will determine the characteristics of the final layered oxide product. Preparation of precursor materials. The precursor materials are then prepared by various methods, such as solid-state reaction, sol-gel synthesis, hydrothermal synthesis, or chemical precipitation. These methods involve mixing the precursor materials in the appropriate stoichiometric ratios and processing them to form a homogeneous mixture of solution. Formation of layered structure. The precursor materials are then subjected to conditions that promote the formation of a layered structure. For example, in the case of layered double hydroxides, LDHs, which are types of layered oxide, the precursor materials are typically dissolved in water to form a colloidal suspension, and then a pH adjusting agent is added to trigger the formation of the layered structures. Heat treatment or annealing. After the formation of a layered structure, the precursor materials are typically subjected to a heat treatment or annealing process to promote solid-state reactions and drive the formation of the final layered oxide product. This step is critical for the crystallization and stabilization of the layered structure. And then the post-synthesis treatments. Depending on the specific properties desired for the layered oxide, additional post-synthesis treatments may be applied. For example, the layered oxide may undergo surface modification, doping with other elements, or annealing under specific conditions to further enhance its properties or tailor its characteristics for specific applications. Characterization and analysis. Finally, the synthesized layered oxide product is characterized and analyzed using various techniques such as X-ray diffraction, XRD, scanning electron microscopy, SEM, transmission electron microscopy, TEM, and spectroscopy to determine its structural, chemical, and physical properties. It's important to note that the synthesis process of layered oxides can be complex and may require specialized equipment and expertise. The specific conditions and techniques used may vary depending on the type of layered oxide being synthesized and desired properties of the final product. Now we switch to another thing here. Uses of layered oxides. So these are just a few examples of the many potential uses for layered oxides. As research and development in materials science continue to progress, layered oxides are likely to find even more diverse applications in various fields. Batteries. Layered oxides are widely used as cathode materials in rechargeable lithium-ion batteries. They have high energy storage capacity, good cycling stability, and high voltage stability, which make them ideal for use in portable electronics, electric vehicles, and grid energy storage systems. In portable electronics, they're in lithium-ion batteries, and electric vehicles, they're in the electric fuel cells, and so on and so forth. Catalysts. Layered oxides are employed as catalysts in various chemical reactions. They can provide high catalytic activity and selectivity due to their layered structure, which allows for easy diffusion of reactants and products. Layered oxides are used in catalytic processes such as hydrogenation, oxidation, and polymerization in industries like petrochemicals, fine chemicals, and environmental applications. We said a little bit about this earlier in the class. Electrochemical devices. Layered oxides are utilized in electrochromic devices, which are used in smart windows, displays, and mirrors. Electrochromic materials can change their optical properties, color, or transparency in response to an applied electric field, and layered oxides with suitable compositions can exhibit good electrochromic performance. Gas sensors. Layered oxides can also be used as gas sensing materials due to their high surface area and chemical reactivity. They can be employed in gas sensors for detecting gases such as oxygen, nitrogen oxide, and volatile organic compounds, VOCs, which find applications in environmental monitoring, industrial safety, and healthcare. Photocatalysis. Layered oxides are utilized as photocatalysts for water splitting, pollutant degradation, and hydrogen production through photocatalytic processes. The layered structure allows for efficient charge separation and transfer, enabling photocatalytic activity under light irradiation. Magnetic materials. Some layered oxides exhibit magnetic properties, making them suitable for applications in data storage, magnetic sensors, and magnetic refrigeration. These materials can have high magnetization values, low corrosivity, and tunable magnetic properties depending on their composition and structure. Thermoelectric materials. Layered oxides can also be used as thermoelectric materials, which can convert waste heat into electricity. They exhibit good thermoelectric performance due to their unique electronic structure and layered nature, making them promising for waste heat recovery applications in industries, transportation, and energy harvesting. Coatings. Layered oxides can be used as protective coatings due to their high hardness, chemical stability, and wear resistance. They can be applied on surfaces of materials to enhance their durability, corrosion resistance, and thermal stability in various industries, including aerospace, automotive, and marine. And here are some reactions of oxides.
Chemical reactions tell us about a metal's reactivity. Mix zinc with copper oxide, lay the mixture out on a heat-proof mat, and heat one end. A reaction soon begins and spreads through the mixture without further heating. Zinc is reacting to form zinc oxide, which is yellow when hot. But what else has formed? Place the remaining solid in dilute acid, and after a few minutes, you can see pure copper. Zinc has reacted with the oxygen in the copper oxide, leaving copper behind. So zinc is more reactive than copper. Aluminium is another reactive metal. Its reaction with iron oxide gives out a huge amount of energy. A measured amount of aluminium is mixed with iron oxide and placed in a small pot. Potassium permanganate is sprinkled on top, and glycerol is added. The vigorous reaction between potassium permanganate and glycerol gives out enough heat to start the main reaction. Red-hot molten iron falls into the bucket. The aluminium has reacted with the oxygen in the iron oxide, leaving iron metal behind. So aluminium must be more reactive than iron. This reaction is so effective that it's used on a larger scale for welding iron railway tracks together. Molten iron fills the gap. And a grinder makes it smooth.
So those are some reactions of oxides. There's plenty more. So here's some of my more excited. I use a lot of YouTube videos and online sources. Thank you.